Hello, this is Lecture-5, 6th Sem, Maths 3 by Ramanjan sir. Department of Mathematics, Department of Mathematics. Let us see a few more problems based on discrete and indiscrete topology. So already we discussed problem 1 and 2 in lecture 4, whereas now here in continuation of the previous lecture, third problem, problem 3. If X is equal to set of A, B, C and tau is equal to set of P of X power set of X power set of X is tau is a topology on X, tau is a topology on X. If so, what type of topology is? What type of topology is? What type of topology is? Right, solution. Given X is equal to set of A, B, C and tau is equal to set of X, phi, set of A, set of B, set of C, set of A, B, set of B, C, set of A, C. Then clearly tau is a topology on X and it is a discrete topology, right? So always that set of X, phi and the set of all possible subsets of the given set, both are the topologies. Particularly only set of X, Y is indiscrete topology and the other one is all possible subsets of X is a discrete topology. Next. Right. Fourth problem. Write any three non-trivial topologies on X is equal to set of A, B, C. So this is the question asked in 2018. Any three non-trivial topologies. So let us see that the solution. Given X is equal to set of A, B, C then P of x is equal to set of x comma phi comma set of A comma set of B comma set of C comma set of A comma B comma set of B comma C comma set of A comma C. So these are all the possible subsets of X. Here a few family of subsets of we take, that we will show that it is a topology, and later on it is a non-trivial topology. 2 1 is equal to any 3 they are asking. 2 1 is equal to set of x comma phi comma set of A comma set of A comma C. This is a topology on X. Next, tau 2 is equal to set of x comma phi comma set of A comma set of A comma B. Next, tau 3 is equal to x comma phi comma set of A comma set of B comma set of A comma B. That I will write tau 1 is equal to tau 2 is equal to tau 3 is equal to like that. The topologies now, the topologies, because all the three are topologies, the topologies because these are all topologies on X. The topologies tau 1 comma tau 2 comma tau 3 are the three non-trivial topologies on X. Non-trivial topologies on X. So how many topologies on a set X having 3 elements? That it was written already, whereas I will explain once again how many topologies are existing. The number of possible topologies on a set X having 3 elements are 29, which are including discrete and the indiscrete topologies. And among them 27 are non-trivial topologies. Right. Next definition: cofinite topology. It was asked in 2018, the definition and also a theorem. So what is cofinite topology? if x is a x is if x is an infinite set, if x is an infinite set and see that again I shall explain cofinite topology. If x is an infinite set and tau is a collection of subsets of x which are consisting of phi and all those of subsets of x, so that in that set x is there, phi is also there. The remaining few subsets are there and whose complements are to be finite, then that topology, that tau is called a topology on x, and x comma tau is a topological space. That tau is now is called a cofinite topology. It means whatever the topology having the elements are there whose complements are to be finite. So let us see a theorem based on this cofinite topology. Theorem this is asked in 2018, even this definition also 2018. Let us now statement. State and prove cofinite topology. State and prove cofinite topology. State and prove cofinite topology. So statement if x is an infinite set, and tau is a collection of subsets of x. Tau is a collection of subsets of x consisting of phi and all those subsets of x, whose complements are finite, whose complements are finite, then show that tau is a topology on x. Then show that tau is a topology on x. Then later on, the tau is said to be a cofinite topology. So see that now the proof. We observe that tau satisfies the following conditions. Tau satisfies the following conditions. First one, phi belongs to tau. Second one, x dash is equal to phi we know, which is finite, and x must be belongs to subset of X implies, suppose any set whose complement is finite, that because X dash is equal to phi means phi is always to be finite, because empty set is the finite set, and automatically its complement again X must be subset of X, and that X is to be belongs to 2. Why? Because suppose X belongs to 2, its complement is X dash is equal to phi, that automatically is finite. As the conditions are to be satisfied, its complements are finite, that the given set X belongs to 2. Next, third one. If set of an element G alpha such that alpha belongs to alpha belongs to, and the notation for this is an arbitrary collection of sets in tau, that means G alpha, G beta, G gamma, like that, where alpha, beta, gamma belongs to tau, like that. A few subsets whose collection, whose all the elements are tau, that collection I will take. Then that means G alpha, G beta, G gamma, like that. Then G alpha dash is finite for each alpha belongs to and. That we know, because any element which is in tau whose complement is finite, therefore their intersection of G alpha dash such that alpha belongs to and is finite. Why? Because intersection of finite sets. This is one finite set whose intersection is also to be finite, and whenever it is finite and its union of G alpha such that alpha belongs to A must be belongs to 2. That is, every arbitrary union of sets of 2 belongs to 2. The third condition is satisfied. Okay, because whatever the union go back to the every union of elements of 2 is again a member of 2, like this. Next, fourth one. If G1, G2 belongs to 2, then G1 dash, G2 dash are finite, are finite implies G1 dash union G2 dash is finite. Implies G1 intersection G2 whole dash is finite by De Morgan's law. This implies G1 intersection G2 must belongs to tau. That is every finite intersection of sets of tau belongs to tau. Therefore, tau satisfies all the four conditions on X. Thus, tau is a topology on X, and tau is a cofinite topology. Then we will see a few in the next class. Thank you very much.